Hi there, this is Thomas from Investment Excel. Today I will show you the normal distribution and how it's built in terms of parameters. I will use simulation to show the statistical properties of the distribution and also look at some statistical inference. It's a topic, I would say, on a basic level, at least for the most part of it, but there are some reference to the central limit theorem that could be challenging. If you're not too familiar with the central limit theorem and the normal distribution, I refer to other sessions I have made on Investment Excel. This video and the Excel workbook are both available on the homepage of investmentexcel.com and spotify.com. Let's move on. Look at the normal distribution and just start here because this is the view that everyone knows. This is the classical bell-shaped form, 50% area to the left of the average, in this case 1000, and 50% on the other side. Now the normal distribution is a parametric functionality. That means it's a continuous relationship between what we call on the y-axis the density and on the x-axis the outcome of the stochastic variable. The stochastic variable x, as we most often labels it, is governed by a statistical distribution or model, which is the normal distribution. So you can go in and see, okay, what is the density of getting 1050, 950, and so on. What we know from the normal distribution is that the highest density is associated always with the mean, the center of the distribution. If you might note, or if you note here that this doesn't look continuous, it's just because of the way that I have graphed it in terms of a scatter plot. Never mind. Okay, let's look at a concrete example. I have a true population where it's assumed that the weekly dollar income in the US is 1000 and it has a standard deviation of $25. So a normal distribution that describes the entire US population just from two parameters of a mean and a standard deviation. And this is exactly the distribution that I have here. And here we can actually identify already the 95% confidence interval. Why? It's because we know that a 95% confidence interval is a 2 standard deviation away from the mean in both directions. And as I have 25 as the standard deviation is $50 in each direction from the mean. So 950 and 1050. So this interval here is a 95% confidence interval. 95% of all incomes, all registered incomes in the population is within 950 and 1050. Down here we have the cumulative density function, that goes all the way to 1. So finally, it goes to infinite in principle. So that's the normal distribution for a stochastic variable. Now, what I want to show you now is a very powerful concept called the central limit theorem that states that if we sample from a population, let's just say a true population here, and calculate the average or any linear combination of the population, then we will end up with a new normal distribution with the same mean as for the outcome of the simple observations, not the average, but with a standard deviation that is dependent on the numbers of observations in the sampling. And by sampling, essentially we mean the size of the sample. So in this case, I tried to sample 500 times out of this distribution with a sampling size of 200. So 200 times, so 500 times I have taken a sample out of the distribution and calculated the values. And according to the CLT, the average should be 1000. And the reason why it is not is because it will go approximately closer and closer as I sample more and more. I have only sampled 500 times. So here the 999 I got from taking the average of all the averages of 500 individual samples. And the standard error is calculated by some simple or standard way of calculating the standard deviation. So we take the standard error as we know it and divide by the square root of the sample size. So here are all the samples, and all the samples with its own average and standard deviation. Now I want to see if the distribution of all these samples are indeed normally distributed, or in this case approximated, because these are discrete observations. So I have to build some ranges on the x-axis to put in all the counts, all the number of averages that are within this group, between these two numbers, and so on. So a normal count histogram here, and here are the associated frequency, and we see as we get closer and closer to the mean, we have the highest probabilities. And here we have actual probabilities and not densities, because we are in a discrete universe. And this leaves us with this result, and we see some bell-shaped functionality or pattern. I'll just try to type F9 to activate the random function in the sampling, so we can see with some other new 500 samples, and we see it looks quite good. And the idea is that we actually don't even need a normal distribution to a normal original distribution for the random outcomes, say here, if we assumed a uniform distribution that all people in the US, they had the same income, then the average would also be normally distributed. And we also only need around 30 numbers in the sample. The sample size should only be 30 before we will get some kind of normal distribution pattern. And this is why we say very, very often that it's okay just to take a sample if you like to test something. Say if you like to test the average size, average height within a school, you can just take out 30 people and measure the average. Just make sure that it's a representative sample. Then the average of this school, this average height, will be normally distributed like this, and then based on this we can calculate some statistics, for instance with the confidence interval and the probability that the height is lower than this or higher than this. Normally when you see polling regarding votes, political parties, you often see sample sizes of 1000. But the principle is the same. The assumption when they make these kind of samples and statistical analysis of party popularity, say Democrats or Republicans, it's all about the same. Defining a sample size so that we are satisfied with the confidence interval, so that we can say there's a 95% chance that the Democrats they actually get 60% of the votes, as is the average that we have calculated. The higher the sample size, the lower the risk around, the lower the standard deviation around the average value, and this can be seen down here. So the larger sample you make in your analysis, the more confident you can be in your obtained say average of the sample. But on the other hand, there is always in analysis, in scientific analysis, a trade-off, because it can be a larger task to get information from many people. So you have to find the right trade-off for you between time spending on obtaining the large sample and the statistical inference. Alright, this was the normal distribution. Thank you.